Hello, and welcome to G Fun Facts Online, the podcast where we dive into the fascinating world of science and technology. I am your host, and today we're shrinking things down, way down, to explore a challenge that's heating up the world of electronics and energy, managing heat flow at the micro and nano scale. You might not think about it, but how heat moves in tiny spaces is critical for the next generation of gadgets and green energy solutions. Imagine your super powerful smartphone or your sleek laptop. As these devices get smaller and more powerful, the components inside are packed closer together, and they generate a lot of heat. This isn't just about your phone feeling warm. This heat can seriously mess with performance, reliability, and even how long your devices last. So scientists and engineers are in a race to understand and control this tiny inferno. And guess what? Advanced microscopy techniques are our super cool goggles for this fiery challenge. Speaking of super cool goggles, there's some exciting news. Scientists have recently developed a groundbreaking thermal diffusivity microscope. This isn't just another microscope. It's a game changer. A collaborative team from the Technical University of Denmark, Technion, and the University of Antwerp introduced this innovation, and it's pretty special. Why? Well, for starters, it doesn't require any complicated sample preparation, which is a huge plus. It can also perform incredibly high-resolution measurements on a very small scale. This means we can see how heat disperses in materials more accurately and without damaging them. Think about it. We can observe heat moving in different directions within a material, something scientists call anisotropy. This level of detail is crucial, because even tiny variations in heat conduction at the nanoscale can have a massive impact on a material's performance. This is especially true for thermoelectric materials, the amazing stuff that can convert heat into electricity, or vice versa. This new microscope has already been tested on materials like bismuth telluride and antimony telluride, which are common in these thermoelectric devices. The results? It accurately measured the directional heat flow, giving us vital data to design more efficient gadgets. This is a big leap forward, a faster, simpler, and non-destructive way to understand how materials handle heat. So why all this fuss about measuring heat so precisely? Well, efficient thermal management is a cornerstone for a ton of technologies. In electronics, like our computers and phones, better heat dissipation means faster, more reliable performance. No more frustrating slowdowns, or, worse, devices overheating and giving up the ghost. For energy devices, like solar panels or the batteries in electric cars, controlling heat flow is absolutely essential. It helps optimize their efficiency, makes them last longer, and keeps them safe. Being able to precisely measure and understand how heat moves at the material level gives engineers superpowers. They can, first, select the best materials for the job, whether they need something that conducts heat away quickly or something that insulates well. Second, optimize device design. Knowing where the heat is going allows for smarter placement of components and the creation of efficient pathways to get rid of unwanted heat. Third, enhance performance and reliability by preventing those dreaded hotspots and managing thermal stress. And finally, it supports green technologies. Developing materials that efficiently convert heat to electricity or minimize heat loss helps us conserve energy and build a more sustainable future. Pretty important stuff. The new microscope we talked about is fantastic, but it joins a family of other advanced microscopy techniques that scientists use to get a grip on thermal flow. Let's briefly meet a few of them. First up is scanning thermal microscopy, or STHM. Imagine a tiny temperature-sensitive probe scanning a surface. It can act like a nanothermometer or even a tiny heater. This technique can spot hot spots in electronic devices and study heat conductivity in nanostructured materials with incredible detail, down to the nanometer scale. Then there's scanning electron microscopy, SEM, and energy dispersive spectroscopy, EDS. While SEM doesn't measure temperature directly in real time, it gives us super high-resolution images of a material's internal structure, things like tiny defects, grain boundaries, and how different phases are distributed. This is vital because a material's structure, which can change with temperature, hugely influences its thermal properties. EDS then tells us what elements are present. These are crucial for checking if materials can withstand extreme temperatures, like in aerospace engines. Often working with SEM and EDS is electron backscatter diffraction, or EBSD. This technique maps out how crystals are arranged in a material, their phases, structure, orientation, and shape. Why care about crystals? Because their arrangement significantly impacts how heat travels. And finally, there are ultrafast optical techniques. These are used to study energy transport at the nanoscale, especially how heat crosses the boundaries between different materials, something called thermal boundary resistance. By combining these experiments with computer models, researchers get fundamental insights into how heat jumps from one material layer to another, which is a critical factor in how well a device manages heat overall. Now, even with all these amazing tools and progress, there are still challenges. For example, it's one thing to find a new material with great thermal conductivity, but it's another complex engineering puzzle to actually integrate it into a device effectively, especially when dealing with those tricky thermal resistances at material interfaces. They often create thermal bottlenecks. And then there are new, exotic materials, like 2D materials, which have really unusual and direction-dependent thermal properties that need a lot more exploration. So what's next? The future is looking busy and exciting. Researchers will likely focus on developing even higher resolution and faster thermal imaging techniques. We always want to see smaller and see it happen quicker. Improving our fundamental understanding of how heat actually travels in solids, particularly through tiny vibrations called phonons, especially at interfaces and in those complex nanostructured materials. Engineering materials and interfaces to precisely control heat flow. This might involve clever strategies, like aligning phonon band structures or optimizing the chemical bonds between layers. Integrating AI-driven techniques. Artificial intelligence can help run complex simulations to explore transport physics in brand new materials and optimize thermal management solutions faster than ever. And, of course, developing cost-effective and scalable manufacturing processes. It's great to invent amazing things in the lab, but we need to be able to make them efficiently for everyone to benefit. The journey to master heat at the micro and nanoscale is ongoing, and these advanced microscopy techniques are our essential guides. They provide the fundamental knowledge we need to engineer more efficient, more reliable, and more sustainable electronic and energy devices. It's a tiny world with huge implications, paving the way for future technological breakthroughs that will shape how we live, work, and power our planet. And that's all the time we have for today on G Fun Facts Online. I hope you found this peek into the world of nanoscale heat management as fascinating as I did. Join us next time for more amazing insights from the world of science and tech. Thanks for listening.